Thank you. So today we'll be presenting security in depth for Linux software, preventing and mitigating security bugs. So we have three main goals in this talk. The first one is to explain how to implement security in depth and the least privilege principle in your Linux code. The second one is to explain how we design a few sandboxes on Linux. And the third goal is to convince you that good code writing practices and good design can work. So first, quick definition, what's security in depth? So security in depth comes from the principle that a secure application should have some tolerance for mistakes. A single failure ideally shouldn't completely break the security model of your application. So today we will try to address this from a Linux application programmer perspective, and we'll be using Google Chromium and VSFTPD as examples during our talk. So there are many steps you can take towards security in depth. So the first one would be having secure code and reducing the number of mistakes you make and not having vulnerabilities in the first place. Second step you can have is application level exploitation mitigation. So you might have heard about SSP, former Propolis, which is stack canaries to prevent stack buffer overflows exploitation. You've probably heard also about system-level exploit mitigation techniques such as address space layout randomization, non-executability. You might have heard about privilege dropping, which we also call sandboxing in this talk. And you might also know mandatory access control, and you've heard about security updates, right? So in this talk, we will focus on only two steps, which is secure code and privilege dropping. So in the first part, I will talk about process and privileges in Linux in the classical sense, just as a quick reminder. So the privilege model of Unix, in a nutshell, each process has its own address space, and the processor MMU enforces separation of different address space. And in this model, the kernel is a mandatory interface to the system from process perspective, and the process is really the privilege boundary. Usually you associate a privilege with a process. Also, something worth mentioning in the standard Unix security model is root has access to everything, and other users are subject to discretionary access control. So privilege ordering can be important, but usually it's something hard to do. So we'll define privilege ordering by saying if process A has more privileges than process B, if A has access to every resource B has access to. So from this definition, we can say that any process running as root is more privileged than any other process because it can do everything on the system. That's in the general case. Two processes with the same UID and GID may have the same privilege. That's the usual normal case, but we'll see some other cases. And one can generally not compare two processes with different UIDs because usually they will just have access to a different set of resources, for instance, different users on the same machines will have access to different files, for instance. So threads, we've seen that the process was the privilege boundary. So usually there is no possible privilege separation inside a process. We'll see one exception today, which is the seccomp sandbox, which we will introduce later. And there is also another one in Google, which is called native client. Also, debugging is quite interesting because if A can debug, or the ptrace system call, on process B, then A is more privileged than B because it can make B do whatever he wants. So we have, in Linux, we have a few privilege-related facilities. So of course, the most known one is users and groups. So you have many user ID. You have a general UID, then you have an effective UID, you have a saved UID, you have a file system UID. The same for GIDs. And since Linux 2.2, you also have POSIX capabilities, which have been designed as a way to split root privileges into many different privileges. So a definition that will be useful today is confused deputy, a computer program that is innocently fooled to use its ambient authority is called a confused deputy. So for instance, we will see that a lot of the Linux privileges facilities have been thought as to reduce confused deputy problems. So for instance, partial UID switching is mostly useful to avoid this kind of problems. But it's completely useless in case of arbitrary code execution when an attacker has complete control over your process, because if your process can actually revert back and gain its privilege back, so can the attacker who is in control of your process. And only root can use this facility of switching UIDs. Linux capabilities, so as I've said, Linux divides root privileges into distinct units. So for instance, you have capnet row, which allows you to use row sockets. You have also capsysadmin, and you have tons of them, like 20 of them. Capabilities have a few limitations. The first common mistake that you can see usually is forgetting to switch from UID 0. Even if you drop all capabilities or most capabilities, you have to switch from UID 0. Second mistake is a lot of capabilities are root equivalent. So for instance, there is a capability that allows you to load module into the kernel. So obviously that's root equivalent. So in this case, we say capabilities are only useful for confused deputy problems in this particular case. But you can also make good use of capabilities if you know what you're doing. Also, capabilities are a root privilege dropping facility. You need to be, a normal user has no capability, so he has nothing to drop there. So you can read in the appendix more about capabilities. We're not going to talk too long about that. So changing root, it's probably one of the most used tricks to drop privileges. So it's a very popular way to drop file system access. How else would you drop access to files that are readable by anyone? The problem with changing root is it requires dropping privileges afterwards, because otherwise it's extremely easy to escape from a chroot sandbox, because your root, you can do whatever you want. You can load modules, you can change the network, you can ptrace any process on the machine, so you can easily escape from that. So you need to drop privileges afterwards. Something that is not very, very well known yet is the new namespaces. They came since Linux 2.6.19 and with very recent additions, even in 2.6.26. So it's a courtesy of the Linux containers, which allows you to create many virtual containers on the same machine. And so we'll see how to use them. But in recent kernels, you have clone new PID, for instance, which allows you to get a new PID namespace for your process. Also, another interesting one is clone new net, which allows you to get a new network namespace. And we'll see how we can use that to drop privileges. However, those are also only accessible by root. You have something that has always been there in Linux. It's resource limits. They can be used for security. So for instance, you have rlimit no files, which restricts you from getting new file descriptors. It's a good way to somehow drop access to the file system, but even without getting new file descriptors, you cannot open new files, but you can still rename existing files, or you can still unlink, which means delete existing files. So it's kind of limited, but it can be useful. Also, if you use that for security, you need to put the limit to 0, because if you put a higher limit, then an attacker could just close the file descriptor to open a new one. Something worth mentioning too is the dumpable flag in the process. So Linux supports a per process dumpable flag, and what that allows you to do is to say, okay, I don't want to be debugged. No one should be able to debug me. And so if you have that, if you do that, it's not really privilege dropping. It's more a privilege elevation, because before every other processes could debug you, now they can. So it's a privilege elevation, but it's still useful in this talk, because if you elevate your privilege, you're consequently lowering the other's process privilege. So it's kind of a privilege dropping facility for other processes. We'll see how to use that also later. Mandatory access control is worth mentioning. Linux has several mandatory access control options, SE Linux, Mac, Tomoyo. They offer some flexibility and a lot of options. However, they require the administrator to set up a policy, which is, we'll see, very different from our goal today. So privilege-related facilities in Linux are usually designed to give less privileges to root. And the one which are not designed to only give less privileges to root still require root to use them. So we don't have many tools at our disposal. With those facilities, it's very easy to protect against confused deputy problems, but not against arbitrary code execution. So yeah, now Chris will talk about writing good code.
Okay, thanks, Julien. Let's see some of these facilities in action. So this is mostly a sandboxing talk, but first a few brief notes on one of Julien's points, which is writing secure code in the first place so that there are no vulnerabilities, or at least you minimize the number of them. And one principle we wanted to quickly introduce is that it's been very successful, is that as a programmer, you should always seek to use APIs that are harder to get wrong than they are to get right. And this principle works because programmers are lazy. They'll always follow the path of least resistance. So if your API directs them down a path that happens to produce secure code, you're in pretty good shape. The most obvious example of this has got to be string manipulation. There have been a lot of problems in C, obviously, the classic buffer overflow, which is just due to mismanagement of strings. Whereas if you are using a language like C++, you tend to get that a lot less because the language actually offers a string class by default and will handle all of the buffer allocation and extension and concatenations and so on for you. And this is actually a solved problem even in C, which is a language that's had a lot of these problems, because you can use a C++ like buffer encapsulation in C, and a couple of programs that have done this are VSFDPD, which we're going to talk about in more detail shortly. Another good example we talked about just before lunch was Qmail, a popular mail daemon, and that has had very few problems, if any, with string manipulation and buffer overflows and so on. Your code's got to be readable. If the code's not readable, then there's usually a link between readability and quality of code. And also, if the code's not readable, then how's anyone going to audit it and be confident that they found all the bugs? One other principle, if you're doing something fundamentally dangerous like authentication, make sure all the code's in one place that you can understand the interactions you've got going on. So just to have a couple of examples on the point about APIs that are easy to abuse versus easy to get correct. Here's an example of an API I think is easy to abuse. This function here will actually read something over an SSL socket, and as you can see, it's modeled after the read function in the Unix API, so you would expect it to behave very similarly. So if this function, when you ask some data over the SSL socket, returns 0 to you, what does that mean? Well, traditionally, that means end of file. You're done transferring whatever you were transferring. You can move on now. Unfortunately, if you're on a cryptographic channel, that's not the end of the story. I mean, how did that channel close? Did it close because the remote end actually finished sending? Or do you have a man-in-the-middle attacker that injected a TCP reset and closed the connection down? It happens that both of those cases, one of which is a potential security concern, this API returns 0. And if you really want to find out what happened, you've got to sort of call another API, the sort of really what happened API, that'll tell you if it was a genuine secure shutdown or an insecure shutdown of that socket. So this is the sort of example of an API you want to avoid. And in VSFDPD's implementation of SSL, I got this wrong. I looked at all the other FTP clients and servers, everyone got it wrong. So the principle sort of does seem to hold here. So here's some code random code I dug out that I thought was fairly hard to read. It's sort of iterating over strings, doing lots of length calculations. We've got some pointer arithmetic in there, a nice go-to. So can anyone see a vulnerability in this code? Anyone got an idea what sort of line looks suspicious there? The point being, I don't think there is a vulnerability in that code, but I just can't tell by looking at it. I have to spend quite some time understanding all the different buffer constraints and so on. It'd be much nicer if a secure buffer API were used, which handled all of the allocation automatically. You didn't have to worry about whether your pointer's gone off the end and so on. So on to the more interesting sandboxing related things. We're going to talk about privilege separation. So privilege separation is about using multiple processes in your design. Julien covered the fact that Unix offers a very strong boundary between processes, so they're a good primitive, if you like, to use to make your application more robust. So you sort of want to be looking at one process per privilege level in your application, which sounds complicated, like you might have an explosion of privileges, but typically a lot of good designs can make do with just two processes. We'll see that with VSFTPDs. Obviously, you want to use different users for the two processes, or otherwise the processes can typically just take each other over. Each process should run with the minimum privilege it needs. That's the principle of least security, which Julien, no, what is the principle?
Least security, yeah, I don't remember.
That one, yeah. And obviously these two processes, the trusted end and the untrusted end, are going to have to communicate with each other, and you want to keep that communication simple, both in the sort of messages going back and forth and the way those messages are transmitted. Otherwise, the more complicated that is, the more chances there's going to be a buggy interaction between your trusted and your untrusted end. So let's look at a definite example of VSFTPD. So the motivation for VSFTPD was, this was a long time ago. It was written, I think it started in something like 1999. And at that time, all of the popular FTP servers had a bit of a design error, whereby if you logged in as an anonymous user, which obviously anyone can do without any authentication, and then there was some form of bug, say a buffer overflow in the FTP parsing code, although you were sort of running as an unprivileged user, there's root privilege in the background. So any compromise of an anonymous session, and you've totally lost that machine. And that's kind of unfortunate. And every time a new class of security vulnerabilities would come out, say for example format strings, then you would have these terrible bugs where anonymous FTP servers could get rooted straight away. So that's not such good design, and VSFTPD was started just to see if something could be done about that. So we're going to look at VSFTPD in the attack surface it exposes whilst it's using sandboxing. And the concrete scenario we're going to talk about is an FTP server that doesn't expose anonymous accounts, just has password authenticated accounts, and those logins have to be over SSL. The reason we've thrown SSL into the equation is that it's kind of hard to get the FTP protocol wrong before you've logged in, because you only have to handle accepting a username and a password and checking if it's right or not. Whereas if you add in SSL, you've got the whole SSL handshake, which has got integers and lengths flying back and forth across the network, and that's actually a much larger and more risky attack surface. So the goal is to see what we can do based on our guess that there will be vulnerabilities in SSL libraries that still haven't been discovered. So this is what things look like in terms of processes when you are not yet authenticated to VSFTPD. You've got two processes represented by the shapes there. On the right is the untrusted process running as a nobody, not the real nobody, but sort of the concept of nobody, some user ID that doesn't own anything too sensitive. And in there happens all the risky things, so the FTP parsing and mainly the SSL handshake. And once this untrusted end has got what it thinks is a proposed username and password, it sort of sends them to the trusted end running as root, which has the authority, if that username and password proves to be correct, to sort of kill this process on the right and spawn a new process running as the correct user for that session. The point here being that the stuff running as root on the left is as small as possible and has a very minimal interface to the untrusted side, or all it does is accept a username and password and checks them. So let's say I provide a valid username and password and I get a session now running as Chris. Slightly more trusted, hence the change in color, but Chris may still not have permission to run programs on that machine. He may still be a user that just has permission to download and upload some files. So we've got all of the untrusted stuff still going on in a separate process. So the expanded FTP protocol parsing, more SSL handshakes for the data connections, and so on. And all of the things it may need to do that are slightly privileged, it again asks a new process, privileged process, for those facilities. So one example here is the FTP protocol, if you're following it properly, actually requires that connections coming out from the server originate on port 20, and setting up a socket that has that low port on it is a privileged operation. But you don't need root to do that operation. You just need a single capability. So that's why we can run this new privileged process over here with very little privilege, just sort of the figurative nobody again, but just with a little bit more privilege, which is the single capability to hand out these sockets. So we need to talk about trust relationships between these multiple processes. So we've sort of almost covered this a bit, but if you have a higher privileged process, it's got to really distrust any interaction with the lower privileged process. Let me go back to the unauthenticated slide. A really bad design here would be is if this root process took a message from the untrusted end that said, oh yeah, Chris is here, he gave me his password and it was the right one, honest, and I sort of trusted that as the root process and handed out a session as Chris. That would obviously be very bad, because then a compromised process on the right here could just pretend it was whoever it wanted. So the distrust here is that the password validation absolutely happens in this process on the left. So you've got to handle bad messages from the child. In terms of transmitting a user and a password, that's a couple of strings, so you're looking at some serialization going on. When you deserialize that message, you've got to be very careful not to mess up by, for example, if there are some integers in that deserialization protocol, if you have classic integer overflows or signedness issues and so on, then you could take over the trusted end via a bad message. So you have to be careful there. Or you can have messages that are sort of not garbled, but they're just asking for something that you shouldn't be able to ask for. So one example would be, I just said if the untrusted process said, oh, give me a session as Chris, whereas actually what it needs to do is prove that it knows the password for Chris. So let's look at the attack surface of what a compromised process on Unix in general can do. This represents a non-root process, otherwise obviously you could do anything. So an unprivileged user, a compromised process. So what the attacker will typically want to do is elevate their sort of now local session to a root session via some privilege escalation method. So if you like a two-bug, two-phase approach to get full control over the machine. And the ways they're going to look at doing that are, if they've got full file system access, they're going to be very interested in things like any setuid binaries you've got lying around, because those are a common path for escalation. Any local Unix file system sockets listening also may be interesting to send them bad messages. Maybe we can attack some other processes with the same user as us and take those over. We can attack the kernel API if there are any bugs in the kernel. We could be in trouble. We're running arbitrary code here, so we can try and denial of service the machine via resource exhaustion, not very interesting. We can kill processes, send signals around. Hack the internal network's a very interesting one. So maybe you've got an SSH daemon listening only on the local network. Now you've compromised the machine over the internet. Now you can connect to local host sockets or any other networking services that may have vulnerabilities in them in the DMZ behind the firewall. So VSFTPD has always had some defenses here. It's always had a chroot jail, one method of sandboxing that Julien covered, and that takes out the file system access second escalation component, which is pretty huge. We're assuming that the privileged channel is very careful, and we've been careful enough there, so that's not a significant avenue of attack. Also, because of the way the unprivileged process is set up, it's left in a non-dumpable state. Julien briefly covered that concept. It means that two processes, even though they have the same user ID, cannot trace each other and take each other over. But as you can see, there's still, even though we've gone to a reasonable effort to sandbox something, there's still a few avenues of attack. So with the VSFTPD 2.2 in the default configuration, some of these new Linux kernel sandboxing facilities have been integrated for kernels that support them, and the attack surface has shrunk nicely. So one of the big ones we mentioned, like attacking the internal network. Well, as Julien mentioned, modern kernels have the ability to separate out a process into a new network namespace. And what that means is when you say connect to localhost, it's just not a registered network and you get an error. So that's a very useful reduction in attack surface. A lot of systems, if you log into them, seem to have lying around a bunch of world-readable, writable, shared memory segments. That's unfortunate. Who knows who owns those and what you can do by messing with those. So we also use the new IPC namespace to take that off the attack surface. That's the bottom green cross there. I added some R limits. I'm not particularly interested ever in denial of service attacks, but added some R limits. You can't do a trivial fork bomb, for example. What else? Oh yeah, you can't send kill signals to other FTP processes anymore because you're in the new process ID namespace. So although the processes are sort of there on the machine that you could kill because you have the same user ID, you just can't see them. You just can't look them up by process ID. They're simply not there. What remains is it's quite a large attack surface, is attacking the kernel API. We'll discuss that in some detail on some of the more advanced sandboxes that Julien's going to cover later. So we'll just cover some more subtle trust examples. It's not always obvious when your trusted end of the channel, if you like, is interacting with something that's untrusted. Some examples from the Chromium open source project that's quite interesting. The Chromium browser actually has sandboxed renderer processes so that an evil website who's got a bug in your HTML parsing or image parsing and so on is actually contained within a sandbox. And that sandbox has no write access or no read access to the file system. So there's sort of a conflict there. What about websites that legitimately need to upload and download files to and from the user? So the way this works is upon a request to upload or download a file, the privileged browser kernel brings up a file dialog and asks the user to select a file. And only a file that a user selects in the upload file dialog is sort of registered then as a known file that the renderer can access. So that solves the problem there by making the user choose to send a file to a website. We had an interesting bug that we found and fixed internally in Chromium. If you like, a garbled message attack from one of the slides covered earlier, whereby since the renderer is a sandbox, if they want to play some audio, that's sort of a privileged operation that has to be sent off to the browser kernel. And there was a problem there where if you just sort of lied about how many channels and what the bit rate was of the sample you wanted to play, you could cause a classic integer overflow. So that's been addressed. More subtly, what happens if a renderer crashes? The privileged side of the browser wants to sort of register that condition as interesting and get a stack trace out, and so that we can work out what happened and fixed it. So the interesting state there is, if say the attacker has compromised the renderer and is executing arbitrary code in the renderer, they're actually at liberty to set up the address space for that process however they want, and then sort of fake a crash, if you like, so that when the privilege end attaches to you to dig out a stack trace, you've got a really weird setup in terms of how your memory looks, and so you can try and exploit the parser of the virtual address space or the stack, if you like. Did look at that, didn't find anything. If you find something, drop me a mail. With VSFTPD, whilst putting this presentation together, I actually found a very minor bug, but it does illustrate nicely the subtleties of trust. Let's say you've tried to log in and the password is incorrect. So typically you might delay a couple of seconds. I mean, I'm not a great fan of that. I think if your password's weak, you've got it coming, but VSFTPD does this now. So the question is, someone's made a failed login attempt, bad password. Who does the sleep? Is it the untrusted side or the trusted side? Well, currently it turns out the sleep is done in the untrusted side of VSFTPD, which means that a compromised FTP process could essentially attempt to brute force a password without any rate limiting. So that's a more subtle example of trust relationships there. And I will fix that, even though it's almost not worth fixing. Finally, it's worth talking about patching. I'm just going to re-emphasize in a different way one of Julien's opening points, which was about defending yourself against mistakes in software, because any large piece of software is going to have bugs, and a browser certainly counts as a large piece of software. All of them are huge pieces of code, and millions of lines, most of which are security sensitive or critical. So you're going to have bugs, and some subset of those bugs is going to be security bugs. So you really do need to be looking at not whether a given browser has 10 bugs a year or 100 bugs a year, but what mitigations are there, what mitigations are present there, to take care of the fact that these bugs are inevitably going to be found. So sandboxing is a big one. So Chromium has a sandbox built into it. Another one is how do you get your fixes to users? If a serious bug comes in and you can sort of click your fingers and users are protected, then it's not nearly as serious. So with Chromium, we've tried to have a very rapid update strategy for serious security issues, and that seems to be going quite well.
So yeah, I can go with that. Thank you, Chris. So we'll now be talking about various sandbox designs. So first, I need to define sandboxing. So in this talk, we call sandboxing the ability to restrict a process privileges programmatically without administrative authority on the machine. And we also call it discretionary privilege dropping. So when I say without administrative authority on the machine, I mean that we're not in charge of administrating the machine, but we can allow ourselves to require root privileges, but it's not the same as being an administrator and adding users and adding packaging, etc. If we don't know how the machine works. But we can allow ourselves to have more privileges if needed. You have already in the Linux kernel, as we've mentioned before, you have already mandatory access control. You have several mandatory access control facilities. The problem with mandatory access control is it's for administrators and distribution maintainers. So the good thing is you can write one policy or a set of policies to rule over many programs. So this really puts you in control, and the good thing is you don't even need control over the code. You can set up a policy without control over the code, which is a very good thing. However, sandboxing is a very different perspective. It's a software developer perspective. You write your software, you want to write a sandbox for your own software. You want one code that you wrote and that will work on many machines, that will protect many users, even though they might not use mandatory access control at all. And you want to be able to do that without the need to administer the machine, without the need to push a policy, mandatory access control policy on the machine. So when we talk about sandboxing today, we assume arbitrary code execution. We assume you had maybe a buffer overflow and the attacker has full control over your process. So dropping privileges is completely useless if it's reversible, because the attacker has full control over your process, so he could also revert privileges if he wants to. So we only care marginally about confused deputy problems. So we will show you three different designs. The first one is the ptrace sandbox, which is a VSTPD experiment that Chris wrote. So he will talk to you briefly about that. Then there is the ZQAD sandbox and the seccomp sandbox, which both have been designed for Chromium. So we've seen already that there are very few facilities to write sandboxes on Linux, because most of the privilege-related facilities we've presented are only available to root. And adding new facilities to the kernel would be great. We would love that. We would love to have real sandboxing facilities, but it couldn't be a short-term option. So we had to do something else. So Chris will present you ptrace sandboxing.
Okay, yeah, ptrace sandboxing. So the motivation behind this level of sandboxing is sort of comes in from one of the last picture slides I showed you, where the VSFTP, the attack surface of a compromised FTP process, is sort of shrinking and shrinking until there's this glaring piece left, which is the attack surface exposed by the kernel API, which does have the occasional bug. In fact, Julien finds some of them. So the motivation here is to sort of restrict access to the kernel API such that we sort of avoid unknown kernel bugs. So how it works is you have a process, the untrusted FTP process, which is called the supervised process, and the kernel sort of mediates access to system calls and sort of hands off attempts to this supervisor process, which is trusted, and on a per syscall basis is authorized to make a decision on whether it's going to allow the syscall or not. One of the cons we'll cover of ptrace sandboxing is it does slow things down, and you sort of see why here. When the supervised process is making an interaction with the system, a syscall, and these things are sort of going off all the time, you've got like a message sort of bouncing through the kernel to another process and then bouncing back again a couple of times, and these context switches are pretty slow. So why would we want ptrace sandboxing? Well, it can tightly restrict the kernel API used by the untrusted process, as long as that untrusted process isn't doing too much, and just sort of parsing FTP protocol or parsing an SSL handshake isn't really doing that much, maybe a bit of memory allocation, but no sort of massive interaction with the system. You do have a very high granularity of access control possible. You can do access control on a per syscall request, and also based on the arguments of that syscall. It can actually be used securely. There was an interesting paper recently citing race conditions in this level of sandboxing, whereby a couple of threads can sort of fool the supervisor by changing. Let's go back. Where two collaborating threads in the supervised process can fool the supervisor by sort of changing a piece of memory whilst the supervisor is looking at it. But you can get around that by either avoiding multiple threads or being very selective in what syscalls you sandbox. The code to do this is fairly simple in terms of lines of code, but it's not trivial. Unfortunately, there are a bunch of cons to doing this. Traditionally, this is a really buggy area of the kernel, so let's go back to this slide again. So ideally, just sort of the supervisor supervising the process on the right shouldn't change the behavior of this process on the right, but it turns out there are a ton of bugs in the kernel relating to threads and particularly signals, such that you can actually get into some security bugs and some non-security bugs that just affect your stability. Things seem to be better in recent kernels, but it's been a bit of a landmine area in the past. There are other pitfalls. We'll cover those on a separate slide. I mentioned briefly the performance degradation. One thing that's annoying is if you maintain a ptrace sandbox, it's kind of hard because since you're sandboxing at the syscall level, that's perhaps a little too fine-grained, and you've got a lot of sensitivity here to the exact version of the kernel you're using and the exact version of the libc you're using. If the libc version gets updated, it may sort of try and detect some newer syscalls used in newer kernels, and the moment that happens, you've got to go and update your ptrace sandbox policy. So some pitfalls here. There are the race conditions. As I mentioned, you can sidestep those by not allowing threads. It's a bit more complicated than that. You've got to not allow shared memory, writable shared memory between two compromised processes. Otherwise, even though they're not threads, they can still share the same map piece of memory and collude based on that. So you have to avoid that by carefully restricting the allowed syscalls so that a shared writable mapping can't be set up. Kind of complicated, but the details are in the VSFTPD source code. Or you can not gate access control on pointer-based arguments. It's these pointer-based arguments that incur the susceptibility to this race condition. I've actually forgotten which of those two approaches I went for in the VSFTPD experimental sandbox. I think that's the first one, not allowing shared memory. This next one is pretty terrible, actually, so back to my picture slide again. What happens if for whatever reason the supervisor goes away? So maybe it crashes due to a bug. Maybe it crashes due to a bug that the supervised process can actually trigger that bug. That's pretty bad. Maybe the supervised process puts a bunch of memory pressure on the system and the kernel starts firing sig kills around and kills off the supervisor. In all of these cases, if the supervisor goes away, unfortunately that sort of leaves the supervised process to sort of run away unsupervised. there are sort of some syscalls you can do to sort of try and stop that happening, but there's still remain race conditions, so that's a really unpleasant pitfall. There is a pitfall on 64-bit versus 32-bit syscalls. So if you're running a 64-bit x86 64 kernel, currently in the kernel there are two syscall tables. There are different syscall tables actually for 64-bit Linux versus 32-bit Linux on the Intel architecture. And by sort of fiddling around with how you invoke a syscall, you can sort of fool the supervisor and sort of hit the syscall table it doesn't think you're hitting, and that's kind of annoying. I think that will eventually get fixed in the kernel. You can just about work around it in user space at the moment. If you're interested in the gory details, the VSFTPD source code has a pretty big comment, I think. Also, you can try and desynchronize the supervisor. This is another example of an API that's hard to use correctly because, let's go back to the slide again. When the supervisor gets woken up from an event, it could be a syscall enter event or a syscall exit event, and you aren't really told which it is. So if the supervised process can sort of cause one of those events to go missing, and then you've got a desynchronization going on, and you've probably got a serious breach of policy there. So that's something you have to code around. To summarize p-trace sandboxing, although it does have the potential to increase your security by taking away the kernel attack surface in a sandbox where you've already got a pretty low attack surface, it's kind of probably best avoided just based on the sheer weight of all of these pitfalls. That's why I don't think I'll ever enable this by default in VSFTPD, but the code's there as an interesting academic piece of documentation if you want to go check it out. So don't turn this on in production. I don't even know if it works in the latest version.
Thank you, Chris. I will now introduce the SecureID sandbox, which is the work of Tavis Ormandy and myself. We designed the SecureID sandbox with this idea in mind. From what I've already said, it seems hard to avoid root if you really want to get access to any real privilege dropping facilities. So first, we need to drop access to the file system. So I've mentioned already rlimit no file, which would prevent you from opening new files. But this one is already very limited because you can still delete files, you can still rename files. You also need to prevent ptrace on other processes. Otherwise, it would be trivial to escape your sandbox. If you just use rlimit no file, if you're limited by that, you can just ptrace on another process and escape that, right? So we also need to prevent sending signals to other processes. So there is a lot of reasons to require something more to drop privileges. So if you think about it, just switching UID and GID would mostly solve all of this. And so that's why we designed the SecureID sandbox. So at first, what we had in mind was pure UID-GID switching. So the way we wrote that was we required an administratively defined pool of UIDs, GIDs. So there is no need for etc passwd entries. You just need to say, okay, this range from 1 million to 2 million UIDs is reserved for the SecureID sandbox. Then on invocation, when something wants to get sandboxed and call and execute the SecureID sandbox, which is a SecureID binary, we will search for a new UID and GID, and then we will switch to them. And then we will execute the program to sandbox, and this program will execute under this new UID, GID, and it will prevent it from doing many things, right? So the problem with that is we needed to do that statelessly. We wanted to do that in a stateless manner. So we found a cool trick to do that. So what we did was we choose a random UID and GID in the pool, and then we use rlimit nproc, which restricts the number of processes with the same UID, and then so we restrict, we use rlimit nproc with restricted, and when we make a call to SecureID to switch to this randomly chosen UID, it will fail if the UID is already used. So the good thing is it allows us to do everything in a perfectly stateless way. So the problem with that is it's not ideal because we also would like to prevent a user from exhausting the pool. Otherwise, a user could just call the SatuID sandbox many times until the pool of UID is exhausted, and there isn't much we could do about that. So ideally, we would partition the pool among the different user IDs used on the system. However, that's not very convenient because we didn't want to have to read the user files. We're not administrating the system, so we don't want to have to find out what users are there. We want to be completely independent of the system. So the trade-off we had was to actually partition the pool against hashes of UIDs, of possible Linux UIDs. And so that was a nice trade-off which worked really well because we also made sure that the hash we used would have the following property of not having collisions between successive UIDs. And usually on a real system, what you will have maybe 5 users, and they will usually have successive user IDs. So that works very well. And even if that didn't, it's just a denial of service against a sandbox mechanism. It's not that big of a problem. So that was our first approach. However, even by doing that, we were pretty okay, but still, it leaves a lot exposed. If you only do UID switching, you still have a lot which is exposed. So for instance, you could exploit /temp races, which is a very common security problem. You could also exploit SatuID binaries, which might have some vulnerabilities. And also, it really matters for kernel vulnerabilities exploitation, because usually, if you have, well, pretty often, not usually, but pretty often, when you have a kernel vulnerabilities, so for instance, say a vulnerability in btrace, you will actually exploit it by running SatuID binaries. And there are quite a lot of Linux kernel vulnerabilities that you could not even exploit if you had no access to SatuID binaries. So could we find a way to also get CH rooted? That would be great. But the problem is we are running a root with a SatuID sandbox, so we could imagine doing chroot to an empty directory, switching our UID and GID as I've explained, and then execute the target. But that would not work, because how would you execute the target once you're chrooted to an empty directory? So we thought about many ways to do that. So you could, if you're naive, you could imagine using the chroot capability and giving the chroot capability to the sandbox process. But that would be really bad, because actually the chroot capability is actually equivalent to root. So that would be very dangerous. Also, you could try something along the lines of don't go through execv. You're in the SatuID sandbox, and instead of going through execv again, you will just drop privileges and mmap code. The problem is that would not be convenient, because first, if you're in a SatuID binary, loading libraries or mapping code without going through execv again is very dangerous. It has many problems. You don't clean up your address space. There might be secrets lying in your address space, and there are many other problems. So we tried to find a better way. So could we just give a process the privilege to chroot to an empty directory? That would be good, but can we do that? So we found a way to do exactly that. And that way was to use the following trick, where we would share the process file system structure. So in the Linux kernel, there is a per process, per thread actually, a file system structure. So the way it works is our sandbox, which we can call process A, will spawn a new process B. But we will use the clone system call with the clone fs flag, so that A and B share their root directory, their current working directory, etc. Then process A, which is the sandbox, drop privileges, and B waits for a special message from A. Then A executes a binary, the target binary that we actually want to sandbox. And when this binary this binary running in process A wants to chroot, it sends a message on the socket pair that we've defined before, and then B chroots to an empty directory which also affects A. So basically what you have is you have another process that is root, that has the capability to chroot, and that will do it for you whenever you request it. And the way we gave it that capability is by sharing our FS structure with it. So it has some security implications, because we have a root process B which shares its file system structure with an untrusted process A. So that's very scary. And it's kind of like the confused deputy problem I've mentioned before, except it's way worse. It's like a drugged deputy problem. Because right now we know that our trusted root process B is under bad influence. So we have mitigations around that in case something goes wrong. Normally that should be okay, but we never know. It's kind of a scary situation. So what we do is we drop all capabilities but cap C chroot, because we need to be able to chroot in the privileged process B. Then we set our limit no file to 0, so that the process cannot open any file. And then we still have this problem of process B sharing its file system structure with untrusted process A. But even if A tries to do something bad, B will not be able to open any file. So that's kind of better. So that's what we did, and then we were very happy because we completely dropped file system access by chrooting to an empty directory. So now that we did that, can we improve the first part of the sandbox? And we could, because the first thing you could think about is just you don't even change UID, but you switch to a single common GID, a single common group. And the good thing with that is, since the ptrace check in the Linux kernel is quite tight, it would prevent a sandbox process to ptrace a process outside of the sandbox. And to prevent ptrace among processes inside the sandbox, you can use the dumpable flag that we've mentioned before. But you still have the signal problem, because you still have the same UID as non-sandbox process, and you can still send signals to this. So it's far from perfect. But what we did afterwards was using a new PID namespace with clone new PID. And that actually solves many problems. That actually solves all the problems I've mentioned before. And it's really good because we don't even need to have a special GID or a special UID. We don't need to switch UID or GID anymore. So that's very, very convenient. The only problem is it's quite a new feature, and there is an open question as to how secure it is. You can also drop network access. That's an important thing because the thing is, I've mentioned our limit no file, but what can you do if your process cannot get any new file descriptors? It might be a bit too restrictive. So what you can do is have basically the same idea of having another thread which shares its files with your restricted process. And it becomes a broker for the first one. So the sandbox process would ask the broker process, please open me this file. And the broker process can then take a security decision. Okay, should I allow this process to open this file? Is it okay? Is it a socket? Is it not a socket? And that's works very well. You can also use clone new net, which Chris mentioned in VSFTPD. And that can be used to cut access to the network completely. So Chromium has been adapted to work with this sandbox. The render of Chromium is sandbox with this. We have actually two versions. There is a Chromium dedicated version, which is more lightweight and uses only the clone FS trick I've just mentioned to get chrooted, and the clone new PID. So this is the first level sandbox in Chromium. So there is another level of sandbox, which is kind of research by using seccomp. But so this sandbox is quite complex. So seccomp is something, it's quite old now. It has been introduced in Linux 2.6.10. And what it does is you can, so you're running code and you can say, okay, no, I want to switch to seccomp mode. And when you switch to seccomp mode, what happens is you can only access 4 system calls. So you can only use read, write, exit, and sig return. So exit is obviously to exit your process. Sig return is to be able to handle signals. So what you can really do is read and write. So that's very, very limited, but maybe that might be enough to write a renderer. So that was a question. But the problem is it was designed with pure computing in mind. So it's good in a sense because the 4 systems calls allowed design is simple enough that we can be pretty sure that the design is correct. So interestingly, there were still some vulnerabilities in seccomp, even though it's very simple, as Chris has found a few ones, I think. But at least the design seems correct at first sight. But it's too limited for a browser renderer. And the 2 biggest limitations are that you cannot do any memory allocation. You cannot use mmap. You cannot use brk, which you need to do in a renderer process. And another big problem is you cannot receive any new file descriptor because you would need a receive message for that, which you don't have access to, unfortunately. And the good thing with that is since they share the same address space, even memory allocation will work. But that seems a bit odd because you have actually trusted and untrusted code sharing the address space. And I've mentioned at the beginning of the talk that the process was the security boundary in Linux. So what you have to do is quite complex because the trusted code needs to be in read and execute only memory. Otherwise, the untrusted code could modify the trusted code, which would be an obvious security vulnerability. Then the trusted code cannot access any volatile memory because there is another thread running at the same time that could modify this volatile memory that the trusted code is relying on. So this is quite a challenge. So yeah, here is a figure to understand how it works. So you see the common address space. And so thread 1 is the trusted thread, and thread 2 is untrusted and under seccomp, and it makes syscall requests to the trusted threads. So the problem I've mentioned is the no volatile memory constraint. So this one is quite hard because the code has to be written in pure assembly, and the code cannot even use a stack. But this is kind of too restrictive because you actually really want to be able to use volatile memory. Because many system calls pass pointers to memory, such as open. So if you want to validate a call to open, you actually need to read a pointer. You need to dereference a pointer and read the memory there. So that's the first big problem. And the second one, which might or might not be solved by just stopping the untrusted thread when you have to make a security decision, but that's kind of also a complex design. So also another problem is evaluating complex system calls. So the trusted thread is written in pure assembly, so this is quite hard and impossible. So the solution to that is also quite complex. What you have is, in addition to a trusted thread, you also have a trusted process. And the trusted thread, for whatever it can handle, will ask the trusted process to handle that. And the whole design is very complex. I cannot go into many details now, but if you're interested, you can check this out. The code is open. So this is the work of Marcus Götzsche and Adam Langley, and it's a very complex design. It's also a very good idea to try to overcome the seccomp limitations. And it has very high potential to isolate the kernel from the sandbox program. But for now, it's still work in progress because it's really complex. It has performance issues, and it's not yet enabled by default in Chromium, although it's compiled by default, so you can enable it with a switch if you want to try it. So there are also many other approaches you could have. You could rely on mandatory access control to do sandbox. So if you have just some control over the policy, let's say you just say that everything that is run through /bin/sandbox will automatically be under some policy, then you can kind of have a sandbox relying on a Mac. So it has been done with SE Linux. It's called the SE Linux Sandbox, so you can also check this out if you're interested. You could also even drop, because the good thing in our sandbox is that you can drop privileges during execution. So you can have privileges, set up everything, and then drop privileges. And SE Linux kind of supports something like this with dynamic transitions, so you might also do something with this. But the problem is you're still relying on a policy which has to be put there by the administrator. There is some hope in the future to have real sandboxing facilities inside the kernel. So there was some effort by Adam Langley, which is also co-author of the SecComp sandbox. It was called LSM-SB, and he was trying to use the LSM security hooks inside the Linux kernel to as a facility to be able to drop privileges. So for every hook, you could say, okay, whenever I trigger this hook, I want access to be denied. So this got dropped because SE Linux actually implemented type boundaries inside the kernel. So before, type boundaries were done in userland in SE Linux. Now they are done in the kernel, and there is some hope that in the future it will allow a process to kind of set up its own policy under the condition that it will be more restrictive than the previous one. So that one might happen at some point. Also, some people had an idea of using the ftrace framework, which is not yet inside the Linux kernel, but which might soon be. And by using the ftrace framework, it's kind of like the ptrace sandbox ID, but it's way better because for every system call, you can pass some code that's going to be compiled by the kernel to bytecode, and this bytecode will actually run and check parameters for you. So it can be very, very flexible. So that might also be a good idea. So virtualization, some people use virtualization to separate privilege. The good thing is it doesn't expose the Linux kernel, and currently all mandatory access control systems expose the Linux kernel. So whenever you have a Linux kernel bug, usually you can exploit it even though you have a very restrictive SE Linux policy. So that's a big problem, and virtualization could help to solve that, but it has other problems. Yeah, quick words about attack surface evaluation. So ptrace sandbox or future ftrace sandbox and SecComp sandbox, as Chris has mentioned, allows you to protect your kernel from an untrusted process, which is a good thing because there are quite a lot of vulnerabilities inside the Linux kernel, and that would be actually a good way to escape a sandbox, just to attack the kernel. In the SecureID sandbox, we unfortunately cannot protect the kernel. But the fact that we are ch-rooted still prevents some particular bug exploitation through SecureID binaries. Okay, I will not mention trusted path executable because we are running out of time, but you can read that or talk to us offline after the presentation. So in conclusion, I will say that security in depth is important. And even though Linux has no real sandboxing facilities, it's difficult but possible to write sandboxes on the current Linux kernel without any kernel modification. And Chris has done so inside VSFTPD. It's also the case in Chromium, and we think it's worth it.
So I guess at this point we'll take questions.
We have time for 2 questions. Anybody? Both Chris and Julien will also be available throughout today, so if you'd like to ask them questions, I'm sure you can do so, Chris?
Of course, of course.
Okay, well, thank you very much, Chris, Julien.
Thank you.
Thank you.